Today we'll be working with a turbomachine problem, in this case a centrifugal pump. So the problem statement says, the dimensions of a centrifugal pump are listed below. The pump handles water and is driven at 800 RPM. Calculate the theoretical head and mechanical power input if the flow rate is 1 meters cubed per second. The first step to these problems is usually to draw a picture, which will help us develop the velocity triangles. Okay, so what I did, I drew a picture of the impeller of the pump, which is basically where the blade resides. So we don't have to analyze every single blade in this pump, we just have to analyze one. So I think the first thing that is kind of confusing is actually defining the blade angle. So that's this right here. So we have two blade angles, 160 and 170 for the inlet and outlet respectively. So how the blade angle is defined is relative to the concentric circles of the pump. So let me show you visually. So there is a circle that is concentric with these other circles around this radius. So therefore, if you take the tangent to that circle and you take the tangent to the blade, this is the angle beta. So that defines the blade angle at any position along the blade. So for the inlet, we take the tangent to the inlet diameter and then take the tangent to the blade angle at the inlet, and then that is our beta 1. So this what we could call as beta 1. And then similarly, we could define this angle over here. This would be the angle beta 2. Oh, one thing I forgot to note, I defined the orientation of rotation in terms of this direction. Therefore, when you draw the blades of the centrifugal pump, the blades have to go in this orientation. So the next thing is to draw the velocity vectors at the inlet and outlet. Okay, so the first thing, we're going to define some velocities. The first thing we're going to define is the rotational velocity. So this is going to be u. So this is the velocity at which the pump is going at, the linear velocity. And then we have another velocity defined as w called the relative velocity with respect to the blades. So we're going to call this relative velocity. And then there's one more velocity component, which is the absolute velocity. So this is the velocity if you were taking a reference frame outside the pump and viewing where the water leaves or how the water leaves the pump. So this is based on an external reference frame, while the relative velocity is based on the reference frame of the blade. So that's how you distinguish between the two. Okay, so since we have these things defined, let me just define one more thing from these. You may remember this from dynamics maybe. So the absolute velocity is simply the rotational velocity of the pump plus the relative velocity. So you can think of this as the velocity of the blade plus the velocity of the water relative to the blade. And if you add those things together, you get the velocity of the water. So now let's start defining our velocity triangles. So the rotational velocity at the inlet is always going to be tangent to this circle. So this is going to be tangent. So it's going to look something like that. We'll call this U1. And then the velocity relative to the blade is always tangent to the blade. So it looks something like this. And as we defined earlier, so these should be vectors. So this should be W1. If you add those two vectors together, you get an absolute velocity that looks like this. And then we can repeat the process over here. Blade is rotating in this direction, so its linear velocity points like that. The relative velocity is again along the blade. So this would be W2. This should be a 2. And then when you add these vectors together, you should get something like this. So that's essentially everything you need to solve this problem. From here on out, it's just a geometry problem and a little bit of algebra, and you should get through the process of solving this problem quite easily. The only new thing, or not new thing, but something you've learned in fluid mechanics is the idea of work, which is another way to say the conservation of momentum and how you convert that into work by using angular velocity. So we'll get to that, but that's the only other concept we need to cover. So right now we're just going to look at the inlet velocity triangle. So I'm going to reorient this triangle so that U1, or the relative velocity, is horizontal in my picture. It's the same triangle, but I'm just rotating the picture a little bit. So this picture right here is the same as this picture. And what we know based on the angles given, we know that this right here is the blade angle at the inlet. So we could say that this is the blade angle at the inlet as well. And what we can do is draw right triangles with respect to the relative velocity vector. So what I'm going to do is draw a vertical line downward. It doesn't have to be vertical. I happen to draw V1 and W1 such that it causes the line to be vertical. That doesn't necessarily happen, but in this case, how I drew it, that's what happened. So we have a right triangle like that. So now we have to just define the velocities. So the first thing you want to know is that U1, or the rotational velocity or the linear velocity of the pump, is already given because we're given the rotational or the angular velocity of the pump. So we could write U1 as simply as omega times R1. Next thing we could do is actually define the normal component of the absolute velocity. So this right here is going to be V1 normal. And the reason why we call this normal is because it's entering our control volume. This is all the fluid that enters our control volume. So let me draw out the control volume in our picture. So this is going to be this is going to be our control volume. So it's going to be around the blade, and we're going to view how much of the fluid enters the control volume, which is going to be perpendicular or radially outward of this inlet. So these will be all our V normal. So with that being said, we could define this portion right here as V1 tangential. So now we could properly define V1 normal. So V1 normal is just equal to the relative velocity times the sine of beta, because V1 normal is actually perpendicular to U1. So there's no component of U1 in V1 normal. So we could say that this is W1 sine of beta 1. So let's just solve for the relative velocity. So this is going to be V1 normal over sine beta 1. Therefore, we could define V1 tangential. So this would equal these components. So if you project V1 onto the horizontal axis, so to speak, that'll give us V1 tangential, right? However, we don't have V1 tangential, so we could use these two other velocity vectors to find V1 tangential. So what we could say is that if we project W1 onto this axis, and then if we add that projection to U1, we should get V1 tangential. So that should equal U1 minus W1 cosine of beta 1. And since we defined W1 up here, we could write that in our equation. V1 tangential equals U1 minus V1 normal over the tangent of beta 1. And simply all we do is repeat the process at the outlet. So again, I'm going to draw the U vector in this direction. W vector is going to look something like that. The absolute velocity vector will look something like that. And then in this picture, this is beta 2. Now I'm going to leave the math up to you guys, but essentially these equations over here are the exact same equations for the outlet. So what I can say is that U2 is omega times R2. V1 or V2 tangential is U1 minus V2 normal of tangent beta 2. So you get exactly the same equations if you follow this process. So let's just start plugging in numbers so we can get these velocities defined. Okay, the first thing we gotta do is make sure we have the right unit. So for our rotational velocity of the pump, or the angular velocity, we're given it in terms of RPM, which is 800 RPM. We have to make sure this is in terms of radians per second. So how we convert this, so let me write this out better. So this is 800 rotations per minute. So we have to convert this to radians per second. So this will be, in 1 minute, there are 60 seconds. And then one full rotation is 2 pi radian. Therefore, when you plug this into your calculator, you get 83.776 radians per second. So now that we have that defined, we could actually define the linear velocity of the pump at the inlet and outlet. So U1 is omega times R1. So that's going to be 16.755 meters per second. And then we repeat the process for U2. So for U2, it's 50.266 meters per second. Okay, since we have those defined, our next goal is actually to define this the velocity tangentially, the absolute velocity tangentially. And the reason why it comes down to a momentum balance, because again, our goal is to find the work done, so we could relate the momentum balance to work by applying the rotational or the angular velocity of the pump. So this might be a little bit of a review from fluid mechanics. So we have some velocity component, the absolute velocity component. So this is v1 tangential and then v2 tangential. So based on Newton's law in terms of open systems, what we can write is basically that the sum of torques is equal to the momentum, the rate of change of momentum coming out, minus the rate of change of momentum coming in. So this is momentum coming in and momentum coming out. So this is how it's defined in terms of a rotational system. So let's first define momentum. Momentum is simply the mass flow rate times the velocity outward minus the mass flow rate times the velocity inward. So we could bring out the mass flow rate because there's no mass being created or inputted between or inside the pump. So we could say that the mass flow rate is constant. So this is going to be V out minus V in. Now this is not technically right because we forgot that this is actually a rotational system. So when you define the angular momentum, you have to define it relative to some radius. So this can be R1 and R2. So really V out and V in should be this. So this is not necessarily true. This should be, and this is technically not necessarily true. This is my fault. So this should actually be m dot times v out r1 times the sine of theta 1 minus v in times the r2 times sine of theta 2. This probably makes more sense if I were to draw it out. Okay, so if we have some velocity vector, this is some arbitrary velocity vector, and then this is our r vector. If you want to find the momentum or the velocity that actually causes this pump to rotate, you basically apply V cross R. And then the magnitude of that is simply VR sine of theta. So what we can do, we have things defined in terms of tangential components. We can say that V1 or V times the sine of theta is simply the tangential velocity times R. Therefore, we could say that the sum of torques acting on the system is simply the mass flow rate times the velocity tangentially at 1, or actually at 2, because it's the velocity coming out, times R1 or R2 minus V tangential of 1 times R1. Okay, and this right here, the sum of torques is all the torques acting externally of our system. So basically the pump, the torque of the pump that causes the momentum change or the increase of velocity of the fluid. So we could just say that this is just the torque of the pump times the mass flow rate times VT2 R2 minus VT1 R1. Now another thing is that we have to define this in terms of power. So another way we could write power, I should probably write this in W dot. So the power is equal to the torque times the angular velocity of the pump. So we simply multiply this whole thing by the angular velocity. So let me write that out. So this is m dot times VT2 times R2 omega minus VT1 R1 omega. And you may recognize that R2 times omega is simply the linear velocity of the pump at the inlet or outlet. So we could further simplify this to m dot VT2 U2 minus VT1 U1. And then a final thing that you probably have seen several times by now is that m dot can be rewritten in terms of the mass flow rate, so it's just rho times AV. The final equation for the work or the power is going to be rho times AV times VT2 U2 minus VT1 U1. So therefore we have everything defined in this equation except for the tangential velocities. So that is why we need to find those tangential velocities. Okay, since we have the power defined, our next goal is to find the tangential velocity at the inlet and outlet. So let me rewrite that equation. So for both the inlet and the outlet, the tangential velocity is defined by U minus the normal component over the tangent of beta. And to calculate V tangential, we must have the normal velocity. So our next goal is to define the normal velocity. So to define V normal, we just have to understand what the volumetric flow rate is. So the volumetric flow rate, which is AV, is equal to the volumetric flow rate of the inlet, which is A1 times V1. So this is the volumetric flow rate going through the pump, which is constant. It is equal to the volumetric flow rate going inside the pump or the impeller. Now, the cross-sectional area and the velocity vectors can change, but they have to change in such a way that this is always constant. So what I mean, if A goes up, therefore this velocity has to go down. Now, this velocity 1, or the velocity component, is only the normal velocity to our control volume. So the water is entering axially, which means it's going out radially like this. So this is the water entering the impeller. So our control volume is going to be like this. And it's going to leave the pump like this. So the velocity of 1 in this equation is only the normal velocity to our control volume. So that's all these that are point radially outward. V1 tangential contributes nothing to the flow entering our system. So this just causes rotation around the pump. So the tangential velocities don't really do anything in terms of flow rate. So we actually can define this V1 as V1 normal. Therefore, to find V1 normal, we just solve for it algebraically. The volumetric flow rate through the pump divided by A1. Now A1 can be further defined by the geometry of the pump, so that essentially becomes 2 pi R1, which is the circumference of the inlet, times the blade width, which is B1, which is already given in our problem. So that's the depth of the impeller in terms of this picture. So it's going like into the page, so to speak. And then we take the volumetric flow rate through the pump and divide by that cross-sectional area. And the same thing can be defined for the outlet. So we can say this is AV divided by 2 pi R2 B2. So that's how we find the normal components of the absolute velocities at the inlet and outlet. So let's just plug in these numbers so we could calculate the tangential velocity. So these are the values you get for the normal components of the absolute velocities. So now all we have to do is plug these values into the tangential equation, so then we can plug this value into our power equation, and then we can find the power supplied by the pump. Okay, so this is what we get for the tangential velocities. Now we plug in these values into the work or the power equation. So plugging into this equation, you get 2.211 megawatts of power. I believe the calculations are correct, but if they're incorrect, let me know in the comments below. That's our solution to the first part of this problem, which is how much power the pump provides. Now our next goal is to define the pump head. So let me draw a picture to explain what the pump head is. Okay, so this is the picture of our centrifugal pump. So water is going in axially, and then it's being dispersed outward or radially outward, and it's being rotated in such a way that it goes like that, and it's leaving our pump. So the pump head is essentially how far up we can pump the water before gravity slows it down completely. So this right here is our pump head, and it's defined in terms of meters or in terms of distance. So essentially what we could do is kind of define the conservation of energy with respect to gravity. So let's say we have the work we put in, so the work of the pump, has to equal the potential energy of the water that is being pushed up. So basically the weight of the water, so to speak. So that's going to be mgh, or the pump head. Now, since we're dealing with an open system, we're dealing more with a dynamic equation, meaning this is in terms of power and this is in terms of mass flow rate. So this is mghp. Therefore, if you want to find the pump head, all we have to do is divide by m dot g, and that's another way to write W over rho times AV times G, and that'll give you the head of the pump. So that's a pretty straightforward calculation. So plugging into our equation, what we get is that this equals the pump head is 225.3 meters. So that's how high this pump can push up water based on this flow rate. So that's essentially how you solve for the pump head. It's how much water the pump is able to push vertically upward before it stops going further up. So hopefully that problem was pretty straightforward. There's a lot of fluid mechanic concepts that you need to understand, like the conservation of mass or the conservation of flow rate, understanding how to use the momentum equation in terms of rotational systems, so relating external torques to the change of the momentum flowing in and out of a system, as well as understanding basic definitions such as the pump head. So with that being said, I'll see you in the next video.